So welcome back, everyone. We'll resume this exciting workshop. The next speaker will be Brennan Nichyporuk. I hope I'm pronouncing your name properly. If not, please correct me. So
no,
Brennan is, okay, great. Brennan is a research scientist at Mila and a member of the probabilistic vision group at McGill University. And he develops deep learning techniques for medical image analysis and also works towards the application in industry. So Brennan, thank you very much for agreeing to give a talk. The floor is yours.
Thanks for that introduction. I'll just pull up my slides. Can you see my screen currently?
Yes. Perfect.
Okay. Yeah. So thanks a lot for inviting me, and thanks again for that introduction. Now, this is some work I did with some of my colleagues back in 2021, and we later extended it last year. It's entitled Cohort Bias Adaptation in Aggregated Data Sets for Lesion Segmentation, and is sort of addressing some of the same questions we talked about before the break. So in terms of motivation, so as we know, deep learning methods for focal pathology segmentation detection require large annotated data sets, which are not generally available, which is, of course, one of the big aims of that federated learning hopes to solve. Now, one common strategy to build a large data set is to aggregate multiple data sets together, which in this work we call naive pooling. Now, here we're talking about the ideal scenario where you have all this data available locally, but even then, you may actually see a decrease in performance when you aggregate data due to cohort biases across the data sets. So our goal, therefore, would be to train on data aggregated from multiple data sets while still accounting for individual cohort biases. And of course, we'd hope to see improved inference results over naively pooling the data. Now, next natural question is, what exactly do I mean by cohort biases? Well, cohort biases can be a number of things. I mean, it can result from different acquisition parameters, different scanners, different preprocessing, different patient populations. But let's assume for a second we control for these factors. Do we still have a problem? And in practice, yes, we do. We can still run into an issue because of different labeling styles, different ground truth, in other words. Now, why do we have this issue? Well, determining ground truth is oftentimes subjective. And the boundaries are often very ambiguous. I mean, this is particularly evident, of course, in MS lesion segmentation. And as a result, distribution shifts can take place not only in the inputs, but also the ground truth labels, distribution shifts across data sets. And so as a result, you'll get a unique label style for each data set. Now, here we have a number of different sources or factors that can cause label style. And it's important to note that these aren't just entirely random. I mean, it can be caused by the label protocol, of course, but also things like the goal of a study. For instance, if one hospital is trying to estimate lesion count, they might try to find all lesions, even the small ones. Or if their task is to estimate lesion volume, they might have more of a focus on large lesions. So this can cause an issue. But even if we control for this, we have the same goal and the same study goal and the same labeling protocol. Other factors, such as the underlying semi-automated algorithm. Many methods, of course, are semi-manual, where an expert will correct the output of an automatic method. Changes to that underlying algorithm can cause an issue. And also, of course, rater experience and education, school effects can also cause an issue. So differences in label style across data sets. Why does this cause an issue? Well, models, a naive model, or at least a standard UNet trained on multiple data sets, these models can't simultaneously satisfy multiple labeling styles at the same time. What happens as a result, this precludes things like data set aggregation, as the model ends up just learning sort of an average. And it will often manifest as poor generalization performance on a holdout trial. And of course, in this context, unsupervised domain adaptation methods are of no use, simply because this isn't a distribution. What we're talking about here is not a distribution shift in the input, but actually a distribution shift in the label. So what can we do? Well, instead of ignoring labeling biases, we can model them. So the method we proposed in this work was to use conditional instance norm to condition on the clinical trial identity. And we'll be using multiple clinical trials. I'll go into the data in the next slide. And when we're training the model, with every input sample, we also condition on the trial identity of that sample. At test time, we provide the clinical trial identity and we get a prediction output with the label style of the corresponding clinical trial. So here's the model architecture. It's a standard UNet with a conditional instance norm layer, which means you have different instance norm parameters for each trial. So here's the data. We use 6 different MS clinical trials. We have MRI data, including FLAIR, PDW, T2, T1, and gadolinium enhanced T1. In all cases, there were similar acquisition protocols across the trials. For the T2 lesion labels, the so-called ground truth, experts corrected the output of an automated segmentation technique at the end of the clinical trial. Afterwards, the data, once we got a hold of all 6 trials, the data was reharmonized. And for each trial, we selected 390 patients, and for a total aggregated data set of 2,340 patients. So here onto the results. So the key thing to see here is that by naively aggregating together the data together, which we call naive pooling here, there's actually a performance drop. Why is this? Because the model has no way to know what label style is expected. If the model cannot determine from the image alone whether this sample came from the RRMSA data set or the PPMSB data set, there's no way to output a label in the corresponding style. And what's even worse is this outperforms the single trial models despite having 6 times more data. So we expanded our data set by a factor of 6 and we saw no benefit. So this is, of course, quite troubling. But if we explicitly model the label style of each clinical trial, we can actually do a lot better. And we can do better, a lot better than not only the naive pooling model, but also the individual. We can also outperform the single trial models by a small margin. And the key innovation here is by conditioning on the clinical trial identity, the model, so to speak, knows what label style to output, and therefore can generate a label in the labeling style that's expected. So here's some more results. Here's some visualizations. And we're looking at how a patient would look using a few different labeling styles. So in this case, we have an image from the RRMSB trial, and we fed it through the network with each of the 6 different conditionings. And we can see, and this is the output, as you can see here. Green is true positive, red is false positive, and blue is false negative. And you can see that there are about 2 to 3 label styles here. Specifically, we have this label style in cyan, and we have another in yellow. And there's also a very slight difference between the one in yellow and purple. It's a bit hard to make out. But what's maybe the most interesting here is that the annotation style change between the cyan and yellow groupings was actually, we found out later on, was a consequence of an update to the underlying the underlying automated segmentation algorithms that experts then corrected. That the bias of the underlying algorithm itself was enough to dramatically shift the label distribution. So what I didn't cover was how to identify data sets with similar label styles using SIN parameter analysis. But something like this could be quite useful, as you can identify sort of what, in context of federated learning, which sites might have similar annotation styles. I didn't look at adapting to a new label style by fine tuning on a few labeled examples. This is sort of our instead of just hoping that we generalize well to a new sample or a new data set, you can actually fine tune on a few labeled samples to learn the label style of that data set. And we also had a small part in the most recent extension about modeling image-based detection biases via image conditioning. And you'll be able to find this in our cohort bias adaptation aggregated data sets for lesion segmentation paper published at the DART workshop in 2021 at McGill. And more recently, our extension in Melba, which entitled Rethinking Generalization, the Impact of Annotation Style on Medical Image Segmentation. Now, conclusions. So biases across data sets can negatively impact performance, even if the data can all be aggregated to one location. And this is a problem because there are differences in the distribution of the labels and not just the data. By explicitly modeling individual label styles, it makes it possible to train a high performance model on an aggregated data set. As we showed, if we condition on the label style, we outperform naively aggregating the data together. And we also outperform the single trial baseline models. And given that different data sets have different labeling styles, there are inherent limits on the ability of any method to generalize to new data. Obviously, if there's a different labeling style on a new data set, without knowing something about that labeling style, it's going to be impossible to generalize to it. So this is just something to keep in mind that, you know, if you're getting low performance, and this was brought up earlier in the workshop, if you're getting low performance on particular sites, maybe it's not drastically lower performance, maybe it's 5% or 10%. That gap might actually be due to a difference in label style and not necessarily a difference in the data distribution. And that's wrapping up. I see I'm on time. So thanks so much for your attention, and thanks to our sponsors. Thank you very much.
Thank you very much, Brennan. Very nice talk.
Thank you. And with that, I'll take any questions.
So we have one from Albert Orozco Camacho. Do you see this label style modeling as an approach to address the non-IID data distribution problem that comes inherent to many federated learning settings?
Well, I mean, I guess it, to some extent, it depends what you mean. I mean, here we're talking about a difference in the label distribution. That is indeed what we're doing here. We're outputting something different depending on what the trial identity is. So yes, it is addressing that, but I mean, you'll still get this issue even if every sample is sampled from the same distribution. It is provided that there is this label styling issue. I hope that answers the question.
Thanks.
I have another question for you. Thank you so much. The paper looks very promising. You said something about the true lesions and the false lesions. How do you identify that this indeed is a true lesion?
Sorry, true lesions and the false lesions?
Yeah. What is the basis for forming the true and false? Yeah. I
see what you're saying. Let me go back to that example.
Because
so this
I am actually working on relapsing and secondary progressive, so I'm very much interested in this. Thank you.
I see. So, I mean, in this case, this is with reference. And so again, this gets back to the label style issue. It's with reference to the provided ground truth label, ground truth in quotes. So you're seeing true positive, false negative, but this is all with reference to the whatever ground truth we're provided with. So, I mean, for instance, you're going to see a difference in performance just for this reason. Yeah.
Okay, so you had a pool of images or data sets in an already built pool, right?
Yeah, so we had 6 different clinical trial data sets, and each clinical trial data set was labeled at the end of each clinical trial by a company.
Okay, thank you.
And so we were given these labels, and so yeah, as a result, you know, we're gonna see sort of different results in terms of DICE or true positive, false positive, depending on what the label style is and what label style we choose to output. If we trained a model on a completely different data set, even if it had the same input distribution, but just a different label style, you're going to see very bad performance on another data set with a different label style. So,
thank you.
And
No
maybe
problem.
we have a follow-up from Mike. Oh, you're on mute.
Yeah, I do have a sort of follow-up because I think that's a very interesting question. So, you know, when you aggregated them and you saw that the outcome metric went down, does it necessarily though? I mean, I certainly understand you're basically training these models then to better fit the outcome, the label styles that the training sets or testing sets have, but is there any way that you can kind of validate that against an external measure of validity? Because I mean, there is some ground truth to whether these are real pathology or not. So even though, you know, the metric score compared to what the humans have labeled goes down, it may be that aggregate model still does a better overall job of predicting disease course in the future, or EDSS or something else in MS. So, I mean, is there some way to account for that fact? Do you think that the other trained model would still do that better, or would that, you know, just put the variability between raters back in? Am I making sense there? Sorry, it's
yeah, I think so. Good question. I mean, I do think the aggregated model does generalize better. I mean, I mentioned you can fine tune to a new distribution, but I mean, even if you just take like an ensemble of the outputs, for instance, you end up getting better performance than a model that just has that just models a single trial. Now it is quite marginal in my experience. It's not a 10% jump or anything like this, but it really depends on the data set. And we did do some work where we had an external labeler label a naive pooling model and our model, and we did see a sort of a jump. We didn't end up. It's not something we ended up publishing because the magnitude of this jump is going to depend highly on whatever the labeling protocol is, of course. And sorry, what they did is evaluated our segmentations from both models and made corrections, and then we saw the whatever the difference was between what the expert corrected labels were and what the output from our model was, and there were fewer corrections on the aggregated model. So I think that it would generalize better. That's my intuition.
If I could just jump in for 1 second, also, just to add to that is, it depends on, you're saying that if you aggregated it, it might do well onto a downstream task, right? Like predicting EDSS or something else. We didn't look at that here. But again, the point is that when naively aggregating, you kind of looking on average over the different styles, you could still, for example, for a specific patient, miss some important structures, which may for your downstream task be important. So I think it depends on the downstream task in general. Just
got it. Thank you.
Yeah.
Okay, we have some time for more questions. There is one after from Roman. So your solution consists of 2 models in sequence. One is common model trained in FL, and 2 local model private to each node trained to adapt global labeling into the desired local one. Is that correct? And how do you train these 2 models?
So no, that's not quite correct. Let me go to the architecture. So it's actually it's a single model so this model is actually trained completely locally. There's no federated learning in this example. This is, we have all the data locally. We're training a single model locally. How this differs from a regular UNet is we just have different instance norm parameters for every trial. So we have 6 trials, and that's where, if you can see here, it says auxiliary information. We pass in the clinical trial identity, and for instance, if we pass in the RRMSB trial, it will select that set of instance norm parameters. And so the output of the model will be influenced by the fact that the normalized activations after every convolution layer will be scaled and shifted in a different way. And this is how we model label style. It's called conditional instance normalization. Sorry if that wasn't clear. So a single model, different instance norm parameters for every clinical trial.
Thank you. We have a question from Ashley Pike. In your opinion, should LS, I assume it's label style, use co-registered T1 and flare images?
Could you repeat that one more time, please?
Should label style use co-registered T1 and flare images?
So label style or lesion segmentation, perhaps?
Oh, lesion segmentation. Yes. Probably. I thought about least square at first, but probably right.
I don't know if I can answer that. I mean, in our case, all the data we used was all registered all to the same space. And we had 5 different sequences in our case. Flare, I mean, if you're asking for which one's the most important, I mean, flare is generally the most informative if you have to pick one sequence. Sorry if that doesn't answer your question.
I actually had a similar question about the how you so you mentioned that you use 6 contrasts. I assume they are co-registered, and then a single label per patient is used, right? You don't create one label per contrast. And
oh, I see. So at the end of, so when we combined all these data sets, yes, they're all registered, all 6 clinical trials are all registered to the same template. So they'll all be processed essentially. They'll all be registered the same way, all 6 trials.
And so how, because some lesions appear differently across contrast, like the pre and post GAT, for example, don't necessarily show the same lesion boundary. So how is the ground truth segmentation created in this case?
Well, we have all 5 sequences. I mean, what happens is ground truth is created at the end of every clinical trial by a private company. We didn't recreate the labels. So at the end of every clinical trial, a private company created the ground truth labels, and then what we did is we just reharmonized the data. So renormalized it. I'll mention that I see I didn't put it on here, but every clinical trial included about, on average, 80 different sites. So every clinical trial has quite a few sites there. So we're quite confident that the differences between the trials are not due to site differences alone.
Julian, was the question about how they did labeling? Because we can definitely discuss that after.
Yes.
There's some people on
yeah,
the
I'm sure that's
call.
something we can address.
There are people on the call that could answer that, but they use all the different sequences when they do the labeling at the company.
Oh, during the labeling.
Yeah.
Yes. Sorry, I'm not too well versed there.
They use all of them, and the differences are important. Yeah.
Good. So we have a couple of additional questions. In the interest of time, I think we'll keep these questions. We'll move them to the Miro board for discussion material later, and we're now going to switch to the next speaker. Thank you again very much, Brennan, for your talk.